Welcome back to Gauss's law for magnetic fields. Remember that we previously determined the surface integral of the magnetic field over a closed Gaussian surface equals 0, assuming that there are no magnetic monopoles in existence. The analogous tool for determining magnetic fields in situations with symmetric current distributions is Ampere's law. Of course, Gauss's law for magnetism doesn't help you solve for the magnetic field anywhere in a problem. Ampere's law is going to do that for you in the way that Gauss's law did for electric fields. So I would call Ampere's law Gauss's law, sort of, for analogous symmetric current distributions. It does not involve surface integrals over two-dimensional surfaces or magnetic flux. So this is why it is not Gauss's law. If you reduce the dimensionality of these integrals that you need to consider in Ampere's law from Gauss's law to Ampere's law, you'll find that it involves a line integral. This is a one-dimensional loop integral. We do this line integral around a closed Amperian loop instead of a closed Gaussian surface. So that will be a one-dimensional path C, which encloses a two-dimensional area or surface S. By definition, a closed loop can only define an open surface. You should think about that on your own. The Ampere's law is useful, as you'll see in an example here, for determining the magnetic field that results from a current. We've seen that currents flowing through space produce magnetic fields in the region surrounding the current. If we define an open surface S, which is punctured or pierced by a current, we'll call that enclosed current, analogous to the enclosed charge in Gauss's law. That enclosed current puncturing the surface will produce a magnetic field which is in general pointing in any number of directions along this closed path C. So the statement of Ampere's law, which will apply here to a concrete example now, is that a closed loop integral performed on the path C. What are we integrating? What are we adding up? We're adding up the dot product of the magnetic field and the dl vector along the path around that loop. If we perform this dot product, add up all of the resulting b dot dl's around the loop, it will equal mu naught, the permeability of free space, times the enclosed current. And that will be net enclosed current. So you could have one wire carrying current out of the page as it is here. You could have another over here. Any number of currents in the problem, if they are passing through this open surface, will contribute to the right-hand side of Ampere's law. On page 175 is the simplest application of Ampere's law. Just like with Gauss's law, where we started out with a point charge, here we're going to demonstrate the use of Ampere's law for an infinite thin wire carrying a current I. This happens to be a problem that you know the answer to already. If I say find the magnitude of magnetic field produced by that current at some distance r away from the wire, we know the answer And that's going to help us validate our application of Ampere's law. So here is our infinite wire. It's carrying current. That current is flowing out of the page towards us. Just like with Gauss's law, we need to define a path now that accurately captures the symmetry of the problem. A reasonable choice here would be a circular path around that current I. What is the magnetic field direction or circulation sense produced by I? You apply your right hand rule, your thumb is the current, and your fingers will circulate in the direction that the magnetic field circulates. So we have B field circulating counterclockwise for this current coming out of the page. We've chosen a closed loop. Our Amperian loop C, which is one-dimensional. Just like the Gaussian surface was an imaginary closed surface, this is an imaginary closed loop or path. Ours is a circle which captures this cylindrical symmetry natural to an infinite line. Okay, we've used that before in the context of electric fields. Here, a convention must be defined for our direction of dl. How do I know if dl should be taking us around the loop counterclockwise or clockwise? It depends on how you define positive current. Your dl points counterclockwise if out of the page current is positive. And your dl points clockwise if into the page current is positive. Well, who gets to decide which way positive current is flowing? You do. I would say 90% of the time when I'm solving these problems, I will think of positive current as flowing out of the page. For whatever reason, you might be forced into a situation where you need to integrate clockwise around the loop, and in that case, you must associate currents into the page as being positive. All right, our B.dl is going to be uniform. It's both uniform and easy to calculate on the path C, because we know the B field may only depend on the radius or distance from the wire, lowercase r. This current puncturing the open surface S, that's a two-dimensional surface, bounded by the closed loop L. Let's work the left-hand side of Ampere's law first. We have the closed integral over the path C of B dot dl. Just like with Gauss's law, you're going to have to show every step and justify each simplification here. So we'll do the dot product first, always. That's the magnitude of each vector times the cosine of the angle between them. In our case, that angle is 0 everywhere because B is parallel to DL. So this equals now magnitude B closed path integral over C dl. Why was I able to take the magnitude of B out of the integral? Because B is uniform on C. Our left-hand side starting to look pretty straightforward. All that's left is to add up the length, infinitesimal length dl, around a circle. Well, that's the circumference, and I'll accept the step going from here to here. That's going to be 2 pi r, or you can prove it to me that the dl is r d theta. Technically, as a vector, it's pointing in the theta hat direction. If you were to integrate its magnitude around the circle, you'd be integrating r, which is not dependent on theta. From 0 to 2 pi, that's just the circumference. Okay, back to the right-hand side. Now that we've finished the left-hand side, we have permeability of free space, current enclosed. For us, the amount of enclosed current is plus I. It's plus because we integrated counterclockwise around the loop. So the same way you did with Gauss's law, you will say the left-hand side equals the right-hand side, or B times 2 pi r equals mu naught I. And we have determined the magnitude of the B field as a function of the distance, lowercase r, from the wire. And we know that this is a vector field. It's circulating counterclockwise around the wire. You've seen and derived this result once already using the Biot-Savart law, where we computed the magnetic field for a finite length of wire, and then we stretched out the wire to have infinite length, obtaining this result here. So our first application of Ampere's law has been verified.